Hello, and this video is on lesson 4-3, transforming the absolute value parent function. So this is on page 65. Here the learning targets are to identify the effect on the graph replacing f of x by f of x plus k, k times f of k times x, and f of x plus k. Find the value of k given these graphs. So in the previous lesson, we learned how to graph the absolute value function, which was basically a piecewise defined function. Remember f of x, the equation for this was x or negative x if x was less than 0, and then it was x if x was greater than or equal to 0. So it says here the absolute value function f of x is equal to the absolute value of x is the parent absolute value function. Recall that a parent function is the most basic function of a particular type. Transformations may be performed on a parent function to produce a new function. So let's take a look at some examples. So when we graphed this absolute value function in lesson 4-2, basically at the origin we had the vertex, and then the graph that we got was very even shaped. It was basically a V, and so that's how it looked like. Now a really shorthand way to write this function is just basically this. So this right here is the same thing as this. Now, what happens when we add, multiply, subtract numbers to this function right here? So that's what we're going to do. We're going to look at all these different types of transformations. So here we have the absolute value of x plus 1. We need to go ahead and graph this. So I showed you guys on the calculator how to do this. So if we go to the home screen, click on the graph. In order to graph a piecewise or a absolute value function, you click this symbol here in the red, and right here highlighted in blue is our absolute value function. So when I press X here and I press enter, you can see that there's my absolute value function right there. And if I press tab, and this time I want to go ahead and do the first question, absolute value of x plus 1, what I'm going to get, and it's very important that you put that plus 1 outside the absolute value. Can you see what happened to it? The vertex is no longer at the origin. It moved up 1 unit. So this is what we have here. Right there. So what is the transformation here? Well, the transformation is, it was a vertical translation. Here's my graph again, right there. It's a vertical translation which moved the graph up 1 unit. Here, when I graph this, it's going to give me something else. So what I actually had you guys do is I gave you guys a worksheet, and as you can see here in black is the parent function, and I had you graph all of these, and you guys use your calculators to do that. When we graphed this graph right here, this was basically the graph moving up 5 units. So the transformation, describing the transformation of this is a vertical. It was translated up 1 unit. That's how you describe this transformation. The vertex is at 5. So as you can see, we started the vertex at 0. The parent function always has the vertex start at 0, 0. And so it changes, the vertex changes here. But something important here is that the shape stays exactly the same. And so this is what I had you do for all of these. We had 10 different graphs, 10 different functions, and that's what I had you do using your calculators. Here were the transformations in a random order, and I had you guys match the ones that went with the correct graph. So the first one translated up. I got this one wrong. It's not up 1 unit. I was looking at the book. It's translated up 5 units. So we already used this one. Let's take a look at this one. When you put this in your calculator, it's going to be translated down 5 units. The vertex changes and the shape stays the same. Now notice the difference between this one and this one is that the negative -5 is outside the absolute value. Here we have it inside. How is that going to change our graph? Well, it turns out that it moves the entire graph to the right 5 units. When you put this in your calculator, it's going to be translated to the right 5 units. Again, the vertex changes, it went to the right, and the shape stays the same again. Here, when we add 5 inside the absolute value, the graph shifts 5 units to the left. So it's translated 5 units to the left. Vertex changes and the shape stays the same. Now we start getting to some interesting ones. Here we have a negative inside the absolute value, outside the absolute value. When you put this in your graph, we put that negative on the outside. Take a look what happens. It becomes flipped over. It's basically flipped, or another word for flipped is that it's reflected across which axis here? Well, it's reflected across the x-axis. And as you can see, the x-axis is acting like a mirror, and across that, the shape is a mirror image. And so the vertex here does not change, it stays the same, but the shape also stays the same. It's just basically reflected. Now, what is the difference between this equation here and that equation and this one? Well, it's the placement of the negative. The negative is on the inside of the absolute value. So let's see what happens when we put it on the inside. There it is. But wait, is there anything different from the parent function? Let's compare them. Okay. Well, here is the parent function in red, and here's the next function in blue. Can you see that they're exactly the same thing? actually this graph right here. It overlaps exactly the same, the parent function. So what can be going on here? Well, if we have the negative on the outside, it's reflected across the y-axis. So use your intuition. This is going to be reflected across which axis? It's going to be reflected across the y-axis. And if the y-axis acts as a mirror image, can you see that it is in fact being reflected across the y-axis? The left side is a mirror image of the right side. So basically it's just flipping over the y-axis, but you get the same graph. So the vertex here stays the same and the shape stays the same as well. Now we start getting into some interesting transformations. Here we have 5 times the absolute value of x, and when you graph this, here's how you can graph this without using a calculator. Basically, that tells you what the slope is. Can you see in the parent function how the slope is 1? You're rising 1 and running over 1. Basically, it keeps on doing that, keeps on doing that, keeps on doing it. And basically, to get the other side, you just basically flip it over, and that gives you the same graph for the other way. So if I wanted to graph 5 times the absolute value of x, that means that my slope is going to be 5 over 1. So if I rise 5, 1, 2, 3, 4, 5, and I run over 1, here's my new point. 1, 2, 3, 4, 5, run over 1. When I connect those dots, there is my new graph. And basically, to find my other side, I just have to flip it across the y-axis. And there we go. This by the way is called a vertical stretch. What factor do we stretch it by? Well, we stretch it by a factor of 5. Vertical stretch factor of 5. Now, why is this called a vertical stretch? Well, if you take the parent function and I begin to stretch it vertically, take a look what happens. Let's see here. Let me make this smaller. So if I stretch this graph, and I stretch it further and further and further, can you see how stretching it vertically makes the graph narrower? And if I stretch it just enough, I begin to get the shape that I graphed in red. And so this is why it's called a vertical stretch. But let's go back to how we had it before. There we go. That's it. That's it right there. Alright. So notice that the vertex stays the same when we have vertical stretch, but the shape changes here. It changes. A very important condition to have a vertical stretch. In this case, here's the mathematical notation for it. A is 5. In order to have vertical stretch, A has to be greater than 1. So you could have used 2, 3, 4, 5, 6, 7, all the way to infinity. Alright. Now, what is going to happen if I have the 5 on the inside? Let's go ahead and compare those. So let's say for the first one, I have a vertical stretch factor of 5. There it is, the graph in red. And for the second one, I have the 5 on the inside. What happens here? Well, my vertical stretch factor of 5 is in red, and now I have this where the 5 is inside the absolute value, and overlaps exactly. So again, you can see that I have a slope of 5 when I graph this, like that. The vertex stays the same and the graph and the shape changes. Now, because the 5 is on the inside of the absolute value, we're not calling this vertical stretch, we're calling this a horizontal shrink factor of 1/5. So anytime you have a number on the inside, it's called a horizontal shrink. Every time you have a number on the outside, it's called the vertical something. So here are numbers on the inside, horizontal. And also the important condition for this is that a is larger than 1. So as you can see, here's the mathematical notation. A is 5, which is larger than 1. So it is a horizontal shrink, factor of 1/5. Now, why is it a horizontal shrink? Why do they call it horizontal shrink? So can you see this time, instead of stretching it vertically and moving it vertically, we're actually moving it horizontally now. And when I shrink it horizontally just enough, can you see how these graphs are going to be exactly the same when I shrink it horizontally? So there it is. That's why it's called a horizontal shrink. I'm moving it horizontally and I'm shrinking it. Not stretching it, I'm shrinking it. And so that's why it's called horizontal shrink. And basically, to graph this is your slope. And because I am moving it horizontally, the factor is going to be the reciprocal of whatever number this is. Okay. Now, notice that when we said that if we have the number on the outside, it's going to be a vertical something. And if it was a vertical stretch, that means a is larger than 1. What if we have a number that is a that is larger than 0 but less than 1? Well, again, this is going to be my slope. My rise is going to be 1, and my run is going to be 5. So here is my new point, and here's my other point. When I connect those dots, take a look at what happens to my graph now. The vertex stays the same, and the shape changes. This is not going to be a vertical stretch. Instead, this is a vertical shrink by a factor of 1/5. Why is it vertical shrink? Well, if I move the graph vertically, you can see that if I shrink it just enough, both of these graphs will be just the same right there. So this is whenever, here's the function notation, whenever a, in this case we have a is 1/5, which is between 0 and 1, it's always going to be a vertical shrink. Remember, the number is on the outside, so it is vertical. And the factor is going to be 1/5. Now again, my slope here is 1/5, so I'm just going to have the same graph that I just did, which looks like this. The vertex stays the same, the shape changes. And because this number is on the inside the absolute value compared to this one, we're not going to be calling it vertical. It's going to be a horizontal. Can you guess it? Horizontal what? Horizontal stretch. by a factor. Now remember, the factor is always going to be the reciprocal for horizontal. So for horizontal, the factor is always the reciprocal. So in this case, horizontal stretch factor of 5 over 1, or just basically 5. Now, why is this called a stretch, horizontal stretch? Well, it's because I'm moving the graph horizontally, and then I am stretching it. So if I stretch it horizontally, can you see how eventually I'm going to end up with a graph that I have in red, which is right there. So that is horizontal stretch. Again, it's horizontal because the number is on the inside. There we go. Alright. Example A, describe the transformation of g of x is equal to 2 times the absolute value of x plus 3 from the parent absolute value function, and use them to graph g of x. So notice all these examples here that we just graphed and described. We basically had only one operation for each of them, one transformation. So each of these are just a single transformation. Now you can have more than just one transformation going on in your function. Here in this case we have 2 transformations. Basically, in order to discover what they are, this here is basically a combination of this and this. These put together make this function right here. And so you can use your charts, and notice here we have the number on the outside, which is an example of this, where we have a 5 on the outside. And so in the example that we are doing, this is going to be a vertical stretch factor of 2. So vertical stretch factor of 2, which is described here. And then, since we are adding 3 on the inside of the absolute value, we just look at an example that looks like it. We're adding here. It's translated to the left. So in my example, this is going to be translated horizontal translation to the left by 3 units. 3 units to the left, which is basically here. And so all you have to do now is, first what you want to do is move the vertex first. So which one of these moves the vertex? Well, for vertical stretch, the vertex stays the same, but for horizontal moving to the left, the vertex changes. So because the horizontal translation moves the vertex, we have to do that first. And so that's what we do here. We move it to the left 3 units, and then after we move it to the left 3 units, we can go ahead and make apply the vertical stretch, which means to basically have a slope of 2, which is to rise 2, run over 1, rise 2, run over 1. And so my graph looks something like this, which is what we end up here. Okay, and finally the last thing I had you do was do lesson 4-3 practice 15 through 19. Let's see if I missed anything here. Okay, well, that's it for lesson 4-3. Thank you for watching.